Hello, I'm Ramanpreet Singh Pahwa from ICRA A-Star, and today I'll be talking about our A-Star 3 dataset for autonomous driving in challenging environments. So before I start, I want to quickly go through the agenda. I'll be talking about the motivation behind the problem statement. I'll be talking about the data collection annotation and follow that up with data statistics. I will show some comparison and analysis on our data and follow it up with context. So there are a lot of AV data sets out there, such as Kitty, A3D, and new scenes. However, most of these data sets are relatively simple scenes. They have low scene diversity or low density data and usually captured in daytime. This results in training and benchmarking, which will lead to lower accuracy in real world setting, which may make it unsafe for the public. So what is required for a real data set is collecting data at different times, such as day and night, collecting it at different weather conditions, such as when it's rainy, when it's sunny, when it's cloudy, diverse scenes, highways, tunnels, car streets, and car parks, and either high density or low density data. Some of the highlights of our data sets are that contains high density data, it is publicly accessible, contains heavy occlusions, also contains a significantly lot of night data, has 7 classes for annotations, contains 230,000 3D annotations, and has 39,000 annotated frames. So we used a Toyota hybrid to collect our dataset. We mounted a LiDAR along with 2 color global shutter cameras on either side of the LiDAR. And because we collected the data in Singapore where it rains quite frequently, we covered these cameras with a waterproof casing to avoid situations when it's raining a lot. To annotate the data, we developed an annotation tool that loads the synchronized LiDAR data and the 2 color camera data together, and the user can annotate the data in 3D while using the 2D images as a guide if needed. So our data set is captured at different times and at different weather conditions. 17% of the frames contain high object density. About 25% frames come with heavy occlusions. We have 39,000 annotated frames, out of which 30% frames are night data. And we have 230,000 3D bounding box views for the front view. We annotate our data at 0.2 hertz, which means 1 frame every 5 seconds, driving at 40 to 70 kilometers per hour. This results in very high scene diversity compared to other datasets. To show you our dataset collection in Singapore, the blue lines over here is the trajectory of our autonomous vehicle while collecting the data. The red overlay you see is the new scenes data that is collected in Singapore. So hence our dataset basically covers various highways, neighborhood roads, tunnels, urban and suburban areas, industrial, STP car parks, and coastlines. We collected our data majorly in 2 months, March and July, which covers both the rainy month as well as the dry month. 4 hours worth of data is covered every day on an average, and as I mentioned, we are driving at around 40 to 70 kilometers per hour. So 55 hours worth of driving data was collected, which resulted in 39,000 annotated frames. We follow the same protocols as Kitty, and each bounding box comes with 2 additional attributes, occlusion and truncation. Occlusion over here is either fully visible, minor occlusions, major occlusions, or unknown. Now I'll talk about some of the statistics of the data. So we compare our data set with Kitty over here. You can see the Kitty dataset kind of caps out at about 20 to 22 annotations per frame. However, for our dataset, there's certain frames that have as many as 40 to 50 annotations. And we have more than 100,000 labels for cars, more than 10,000 for trucks, pedestrians, vans, buses, and motorcyclists. Over here, we show the number of points in each of these labels. So you can see that for trucks and buses, they on an average they contain more number of points than other classes because they're bigger in size. And buses and trucks also have significantly lot of labels that have a lot of points even when they're minor or major occlusions. So in this figure, we show different occlusions for different classes. For cars, 70,000 labels have absolutely no occlusion and about 30,000 each for major and minor occlusions. Trucks and buses, because they're bigger in size, the minor and major occlusions are actually quite a lot in terms of number. However, for pedestrians, motorcyclists, and cyclists, because these are very small in size to begin with, major occlusions, you're not in major occlusion issues, you're not able to see these classes, and hence you see very little labels for that. Over here, we show the 3D bounding box orientation. 0 radians over here refers to the cars in front of us. Minus 90 degrees refers to the cars going from left to right, and plus 90 degrees refers to cars going or other objects going from right to left. One curious observation over here is that we see cars going from left to right has more labels than the other way around, and that's because we use our left camera as the major deciding factor, and the left camera will see more traffic that's going from left to right than right to left, resulting in more number of labels for that particular angle. For benchmarking, we look at 3 major algorithms. F.net looks at 2D images first, figures out the region of interest, and only then looks at the 3D data to improve these to come up with 3D bounding box predictions. Point RCNN, on the other hand, only looks at 3D data and creates these accurate 3D bounding box predictions. AVOD, on the other hand, tries to use both RGB images as well as the bird's eye view from 3D points, uses a 2D CNN to come up with these region of interest and fuses them together to come up with the final 3D bounding box. So we benchmark using different distributions. First of all, we look at a dense subset, which we define as having more than 10 objects for both Kitty and A3D. We roughly use about the same amount of data. For Kitty, we use their protocols of about 50% train and 50% val. For us, we use 5.2K for train and 1.5K for val, and we evaluate using point RCNN. What we observe is that even when we train on A3D and validate on Kitty, we are actually able to outperform the models when trained on Kitty and evaluating on Kitty, which shows that our data set is very comprehensive and covers most of the ways that the other data set also covers. We also want to investigate how much additional training data is enough and what is the impact of increasing different density data. So over here we look at 3 different subsets, low density data, high density data, and a mix of both. So what we observe is that for low density and high density, the MAP kind of caps out even when we increase the size of our training set. However, for mix of, we actually do see a significant increase in the accuracy. Over here, we compare our results for day-night versus nighttime, and we look at F.net, which, if you remember, looks at 2D data first and then only looks at improves it in 3D, while AVOD looks at simultaneously both 2D and 3D together. We used a mask RCNN model from scratch as our 2D detector, and our day-to-night ratio data is about 2:1. So what we observe is that for F.net, if we add night data, which is when we only looking at night data, or when we're looking at both night and day together, the results kind of don't work very well because night data kind of adds more noise. If you see over here that the model trained on day data is actually the best for both day and a mix of day and night. However, for AVOD, when we train on both 3D data and 2D data together, we observe that models trained on both day and night is actually able to work pretty well and outperform models when they're only trained on day or night alone. So this kind of gives us this consistent performance that we're looking for. However, we also note that some specialized models can achieve comparable performance in their own modality. In conclusion, we propose a novel multimodal A3D dataset for detection tasks in challenging environments. Highly complex and dense data improves the robustness and accuracy. Best performance is usually obtained when training on a combination of low density and high density samples. Performance of models in different conditions and times of the day is correlated with training in the respective weather and lighting conditions. In future, we want to do a more extensive evaluation of novel detection algorithms on A3D and the current existing AV datasets. We want to develop more accurate algorithms for 3D object detection tasks in real-world settings, and we also want to explore other problems such as terraining, 3D construction, traffic light detection, etc. Thank you for your time. Any questions can be emailed at this following email address. Our code and the dataset is available at the GitHub repository here, which can also be scanned using the QR code. Thank you for your time.